Hello everyone, welcome to CAIE Science, and today we will be solving October November 2022 paper 4-2 of 9701. Okay, so let's begin. Question number 1. Calcium chloride is an ionic solid. The values of some energy changes are shown in table 1.1. Okay, find the lattice energy. Okay, what is lattice energy? It is the energy change when one mole of ionic compound is formed from its gaseous ions. Okay, energy change, energy change when one mole of ionic solid is formed from its gaseous ions. Gaseous ions. Okay. Now use the data in the table 1.1 to calculate the standard enthalpy change of formation of calcium chloride. Okay. You may be helpful to draw energy cycle. So you're all working. Okay. So now in this question, you first have to remember the definition of the standard enthalpy change of formation. So it is the enthalpy change when one mole of ionic solid is formed from its elements in standard states. Okay, so what will be the standard enthalpy of formation of calcium chloride? this calcium chloride this is calcium chloride. Okay, so the standard enthalpy will be when solid calcium will react with chlorine gas to form calcium chloride. Okay, so this is going to be enthalpy change of formation of calcium chloride. Okay, now you have to calculate the value of enthalpy change of formation. Okay, so for this we will draw a energy cycle. So now you know that the standard enthalpy, lattice enthalpy, is the enthalpy change when one mole of ionic solid is formed from its gaseous ions. So let's say if I write here calcium 2 plus ions in gaseous form plus Cl minus ions in gaseous forms, if they react they will form this calcium chloride. So this is going to be in lattice energy, right? And you are given the value of lattice energy of calcium chloride, which is negative 2237. Okay. Now you have to convert this calcium solid into this calcium 2 plus gaseous ions. So firstly we will atomize it calcium to change it into gaseous. So this will be calcium gas, and this is the standard enthalpy change of atomization of calcium. Okay, and its value is plus 193. Okay, so 193. Now you will convert it into calcium 1 plus. This is the first ionization energy of calcium, and then second ionization energy of calcium. Okay, so the first ionization energy of calcium is plus 590 and the second ionization energy is plus 1150. Okay, so now uh, for the chlorine you first have to break the bond, this Cl bond. Okay, and the bond energy for this bond is you are not given the bond energy of this bond, but you are given the standard enthalpy change of atomization of chlorine. Okay, so the bond energy is actually uh, standard enthalpy of atomization multiplied by 2. So if you multiply this 121 multiplied by 2, so this is going to be the bond energy of chlorine. Okay, chlorine. So this is the bond energy of chlorine. So you will form 2 Cl, and this is plus 2. Okay, now you will there will be a first electron affinity of chlorine, so you will form chloride ion. Okay, and its value is negative 364 multiplied by 2, because there are two chloride ions. Okay, so now your cycle is ready. So let's calculate the standard enthalpy change of formation. Okay. So 193 plus 590 plus 1150 plus uh, so this is going to be 242 plus 2 into negative of 364 and then plus minus 2237, okay, is equals to standard enthalpy of formation. So from here you will calculate the value of standard enthalpy of formation, and final value is going to be negative 790. Okay, this is your final answer. Moving towards next part C. Three possible values of first electron affinity of bromine are shown in table 1.2. One of them is correct. Place a tick by the correct value. Explain your choice. So if you see, what is the first electron affinity of chlorine? The first electron affinity of chlorine is negative 364. That's right over here, 364, which is given to you in the table also. So what will be the first electron affinity of bromine? Whether it will be more negative than chlorine, same as of chlorine, or less than. So it will be less than of chlorine, less negative. Why? Because you can see that in chlorine, the chlorine is small, so it has a greater charge density, okay, than the bromine. Or let's say this is chlorine, this is the outer shell of chlorine, and this is the nucleus. So distance between nucleus and outer shell electron is smaller in chlorine than it is in bromine, okay. So that's why the nucleus attracts the incoming electron more in chlorine than in bromine. That's why for bromine it will be less negative, okay. And you have to remember that the first electron affinity is exothermic, okay. That's why its value is negative, okay. So what will be the reason? You can write that Cl atom has greater charge density, greater charge density, okay. Now moving towards next part D. The enthalpy change of hydration of chloride ions can be calculated using the lattice energy of calcium chloride in the data shown in table 1.3. Okay, define the following terms. Enthalpy change of solution. So what is the enthalpy change of solution? It is the energy change when 1 mole of solid dissolves in water, okay. Energy change when 1 mole of solid dissolves dissolves in water, okay. Or you can also write solute dissolves in water to form infinite dilute solution, okay. This is the full definition. Now what is the definition of enthalpy change of hydration? So it is the energy change when 1 mole of gaseous ions when 1 mole of gaseous ions dissolve in water to form infinite dilute solution, Okay, now moving towards next part, calculate the standard enthalpy change of hydration of chloride ions. Okay, it may be helpful to draw energy cycle. So let's first, you are given the standard enthalpy of solution of calcium chloride, and for the what is the uh, equation for the standard enthalpy of formation. So let's say this is calcium chloride in solid. So you know that the definition of enthalpy changes when 1 mole of solid dissolves in water. So when calcium chloride will dissolve in water, it will form calcium 2 plus aqueous plus Cl2 minus aqueous in aqueous form. Okay. Now this is the enthalpy change of solution. And what is the value of enthalpy change of hydration? It is the when 1 mole of gaseous ions dissolve in water. So this will be the enthalpy change of hydration of calcium ions, and this will be the enthalpy change of chloride ions. And this is what you have to find out. Okay, and you know that one mole of when 1 mole of ionic solid is formed from its gaseous ions, it is the lattice enthalpy, and you are given the lattice energy in the table 1.1, and this is the lattice energy of calcium chloride, which is negative 2237, negative 2237, and the enthalpy change of solution is negative 883, and you are also given the value of standard enthalpy of hydration of calcium chloride, okay, which is negative 1650. Okay, and you have to find the the standard enthalpy of hydration of chloride ions. So it will be 2x because there are 2 moles of chlorides. Okay, so you have to find the value of x. So let's construct the equation. Negative 2237 plus negative of 83 is equals to negative of 1650 and plus 2x. So the x is going to be negative of 335. Okay, 335. So this is the hydration enthalpy of chloride ions. Okay, part E, calcium fluoride can be synthesized directly from its elements. The value of standard enthalpy change of formation of calcium chloride is negative 1240. Okay, predict the value of entropy change for this synthesis. Explain your answer. The sign of entropy change is what will be the, so if you see from this equation, the calcium fluoride is synthesized directly from its elements. So calcium, solid calcium, will react with fluorine to form calcium fluoride. Okay, now if you see from the equation, the fluorine is gaseous, and the order, the entropy of gaseous atoms or gaseous elements, or you can say gaseous particles, is more. Okay, so you can see that the number of gas molecules are reduced. Okay, so what will be the value of standard entropy? It will be negative. Okay, negative, because reduction in number of gas molecules. Okay, and the when entropy increases, the value of entropy becomes more positive. Okay, and when entropy becomes negative, it means that the order of the there is less disorder. Okay, you can write as well. Okay, so the sign of entropy will be negative. Okay, because there is a reduction in number of moles of gaseous molecules. Okay, you can see that the solid is formed here and gaseous molecules are reduced. Okay, now use the value of standard enthalpy of formation given in E and your answer to E1 to predict how the feasibility of this synthesis will change with increasing the pressure. So feasibility, we actually discuss feasibility in terms of this equation. Gibbs free energy is equals to enthalpy change negative T enthalpy change in entropy. Okay, when this Gibbs free energy is negative, the reaction is feasible, and when this becomes positive, the reaction becomes less feasible. Okay, so we will see whether increasing the pressure makes the Gibbs free energy more negative or less negative. Okay, so let's first see enthalpy change. So you can see that the enthalpy change, this is the enthalpy change of formation, is negative. Okay, so let's write it negative here. Okay, then negative sign, then you have T, and you also calculate that the sign of entropy change is also negative. Okay, so the sign is for this is also negative. Okay, so now you can see that this negative becomes positive. Okay, negative and negative becomes positive, and this is your Gibbs free energy. So when increasing the pressure, when you will increase the pressure, increase the temperature, the overall this factor will become more negative, and the overall this value becomes more positive. Okay, this value becomes more positive overall. So when this value becomes more positive, so the Gibbs free energy becomes more positive, so the reaction will be less feasible. Okay, so what will be the reason? You will say the reaction will be less feasible. Okay, increasing the temperature makes this factor more positive. Okay, or sorry, makes this factor more negative, so less feasible. Okay, feasible because because Gibbs free energy becomes positive with increasing the pressure becomes positive. So that's your reason. Okay, moving towards next question. Question number 2. Nitrogen monoxide reacts with ozone. Okay, this reaction is first order with respect to nitrogen monoxide and ozone. Okay, at 298 Kelvin, the rate constant is 11,500. Okay, complete the rate equation for this reaction. So rate equation is K equals to, what is the order of reaction with respect to nitrogen monoxide? It is first order, and also first order with respect to ozone. So this is your rate equation for this equation. Okay, now moving towards next part. A reaction is carried out in which the initial concentrations of nitrogen monoxide and ozone are both 1.2 into 10 to the power minus 6. Okay, calculate the initial rate of this reaction. So initial rate is going to be K is given to you, which is 11,500 multiplied by 1.2 into 10 to the power minus 6 square. Okay, square. So this becomes 1.66 into 10 to the power negative 8. Okay, 1.66 into 10 to the power negative 8. And what will be the units? Okay, so if you see what are the units of K, these are mole minus 1 dm cube and second minus 1 multiplied by mole square and dm cube minus 6, because you can see there is a square over here. Okay, so what will be the units? This mole cancel out with this mole, So this becomes 1 mole, and then dm cube cancel out with this dm cube. So mole dm mole per dm cube per second. So these are the units of rate. Okay, you can also remember these. Okay, the units of rate. This is concentration upon time. So the units of concentration and then unit of time. Okay, the reaction described in A2 is monitored over a period of time. Predict whether or not the graph of concentration of nitrogen monoxide against the time under these conditions show that the reaction has a constant half-life. Explain your answer. So yeah, this question is a little tricky. It told you whether the concentration of nitrogen monoxide against time under these conditions show that the reaction has a constant half-life. So it will have no constant half-life, because the overall, you can see that the overall reaction is second order. First order with respect to nitrogen monoxide, and first order with respect to this ozone. So the overall the reaction is second order. So for the second order, the half-life is not constant. This is constant for the first order. Okay, but some students might think that it told us that draw a graph of nitrogen monoxide only. Okay, so and this nitrogen monoxide has first order reaction. Okay, but you can see that this is not asking for this particular reaction, it is asking for the whole reaction. You can see, so that the reaction, okay, and the reaction is this reaction. Okay, for this reaction the overall order is second order, so you don't have to consider here. Okay, so not constant, because overall reaction is second order. Okay, now moving towards next part. Nitrous oxide decompose into its elements. Okay, at high temperature a small amount of platinum wire is added to the large amount of nitrous oxide. Okay, the reaction follows a zero order kinetics. Okay, the platinum wire behaves as catalyst. Okay, sketch a graph on the axis below of the reaction rate against time for the catalyst decomposition of nitrous oxide under these conditions. So you can see that the reaction follows a zero order kinetics. So it means that the concentration of reactants will have no effect on the rate. So for this becomes a zero order. So what will be the graph? Graph will be like this constant line. There will be no change in rate with time. Okay, the rate will not change. Okay, and the catalyst, it is added in very small amount, you can see. So it will also have a negligible effect. Okay, because the nitrous oxide is in large amount and the catalyst is in small amount. Okay, now moving towards next part. Sketch a graph on the axis below of nitrous concentration of nitrous oxide against time for this reaction. Okay, so for this reaction you are told how the graph will look like if the concentration of nitrous oxide is drawn against time. Okay, so you can see that this nitrous oxide has no effect on the rate. Okay, rate does not change, and if you see, rate is change in concentration, change in concentration on time. So the rate will be constant, so it means that the gradient of this graph will be a rate, and rate is constant, so it means the gradient of this graph will also be constant. Okay, so and you can see that this nitrous oxide, the concentration of nitrous oxide will decrease with time. So how will you draw this graph? This will be like this. straight line. I'm sorry, but you have to draw a straight line over here, okay, like this. Now moving towards next part, platinum behaves as a heterogeneous catalyst in this reaction. Describe the mode of heterogeneous catalyst. You have to remember this, okay, the mode of heterogeneous catalyst and mode of homogeneous catalysts, okay. So for the heterogeneous catalyst, it is the catalyst is in different phase to reactants, okay. So there is adsorption adsorption of reactants onto catalyst surface, okay, catalyst surface, and bonds and reactants weaken, okay, and new bonds are formed, weakened, and reaction occurs, followed by desorption, sorry, desorption of products, okay. Now part 4 suggests a reason why this reaction has a zero order kinetics when the amount of nitrous oxide is large and the amount of platinum is small. So if you see, when let's say this is platinum, okay, and the active sites of this catalyst are these, okay, let's say these are the active sites, and the amount of nitrous oxide is large, so these all active sites will be occupied by some particles of nitrous oxide, but the other will not access to these sites, so the catalyst, uh, you can say, will not work efficiently, okay. So you can say that the all active sites on catalyst surface on catalyst surface are occupied, okay, are occupied, sorry, let's make it occupied, okay. That's why this catalyst will not work efficiently, okay. Now moving towards question number 3. Data should be selected from table 3.1 in order to answer some parts of this question, okay. An electrochemical cell can be constructed from this magnesium half cell and this amino 4 half cell, okay. The standard cell potentials for this cell can be calculated using the standard electrode potential of 2 half cells. Now define the standard electrode potential, okay. Include details of standard conditions used, okay. So the standard electrode potential is the voltage produced of half cell by a half cell compared to standard hydrogen electrode, okay, to a standard hydrogen electrode, okay. And the standard conditions for this standard electrode potentials are 1 mole per dm cube. This is the concentration. The standard conditions are standard conditions are 1 mole per dm cube and room temperature, which is in Kelvin. So 298 Kelvin and 1 atm pressure. You also have to remember the conditions for the standard electrode potential. Okay, the concentration should be 1 mole per dm cube. Okay, and the temperature should be room temperature, and the pressure should be 1 atm. Okay, and this is the voltage when half cell is compared with hydrogen electrode. Okay, and this hydrogen electrode has a electrode potential of 0, 0. That's why it is the standard electrode. Okay, now part 2, complete the diagram below to show an electrochemical cell constructed from the magnesium half cell and MnO4 half cell. Okay, so let's make this magnesium electrode over here. This will have an electrode of magnesium. This is the magnesium electrode. Okay, and then you will have this voltmeter over here, and then you will have the platinum wire, platinum plate over here, because there are ions in MnO4 only. Okay, this is not in solid state, so that's why the platinum will, there will be a platinum plate. Okay, so this is platinum, and in solution there will be MnO4 ions, MnO4, okay, MnO4, okay, and Mn2 plus ions. Okay, and also H plus ions. You can see from the equation that this is the equation. Okay, there will also be H plus ions. Okay, so H plus ions, and in this solution you will have magnesium 2 plus ions. Okay, and you will also have a salt bridge. This is the salt bridge. This maintains the flow of ions. Okay, flow of charge. So this is the salt bridge. Now, okay, label your diagram. Okay, we also have labeled. So this is your complete diagram. Okay, for the this electrochemical cell. Okay, now part 3, use a positive and a negative sign to identify polarity of each of the two electrodes in your diagram. Use an arrow and the symbol of E to show the direction of electron flow in the external circuit. Okay, so which of them will be a positive electrode and which of them will be negative? The positive electrode will be the, let's first find out which one is anode and which one is cathode. Okay, so at cathode, you know that the reduction occurs. Okay, at cathode reduction occurs, and at anode oxidation occurs. So this is the you can say reaction of this half cell is this magnesium half cell. The equation for this magnesium half cell is this, and for the MnO4 half cell is this. Okay, and these values are given in reduction potential. Okay, so the one with the greater value will have a more reduction potential, so it is likely to reduce. Okay, and then other will oxidize. You can see magnesium has the reduction potential of negative 2.38, so it means it is difficult to reduce magnesium. Okay, and the reduction potential of this MnO4 is positive 1.5, so it is greater than this value, so it means this MnO4 will reduce. Okay, and so reduction will appear in this half cell, so it means this is cathode. Okay, this half cell is cathode, and this half cell is anode. Okay, now let's find out the polarity. The one with the so if the you can, let's first see what will happen in anode. In anode, the magnesium will form magnesium 2 plus ions plus 2 electrons. So it means the electron flow will be in this direction. Okay, this will be the electron flow. So the electron flow is from the magnesium to this MnO4 half cell, so it means this will be negative. Okay, because the electron flow is from the magnesium, so it will be negatively charged electrode. Okay, and this will be positively charged electrodes. Okay, you also can remember like this, that in half cell, these cells, electrochemical cells, the anode is negative and the cathode is positive. Okay, and reduction occurs at cathode and oxidation occurs at anode. Okay. Now calculate the standard cell potential. Okay, so this standard cell potential is actually E reduction minus E oxidation. So E reduction is for the half cell which is reduced, so it is the plus 1.52 negative and negative 2.38. Okay, 2.38. So it is going to be 3.90. Okay, 3.90. This is your standard cell potential. Okay, construct an equation for this reaction. Okay, so now you have to construct the equation. So let's first write these equations. Go ahead. Magnesium 2 plus the okay, let's make this magnesium, the one which is oxidized. Okay, this magnesium is oxidized, so we will flip this equation. Okay, so that will be magnesium 2 plus 2 electrons, because this is oxidized. Okay, so we have to write it like this. Okay, we will flip the equation because these values are in reduction potential. Okay, these equations are all in reduction. These reactions are electrode reactions are of reduction. Okay, so we will flip the equation, so it will be magnesium will convert into magnesium 2 plus ions and 2 electrons will be released. Okay, and this MnO4 is reduced. Okay, so this will be like this, 5 electrons and MnO4 2 plus water, 4 moles of water. Okay, let's write it correctly. Like this. MnO4 plus 8H plus 5 electrons, so it will form MnO2 plus 4H 2O. So now you have to balance the electrons, so we will multiply this equation with 5 and this equation with 2. So this will be 5 Mg plus 5 Mg2 plus 10 electrons. Okay, and then you have 2 MnO4 plus 16H plus 10 electrons, and you have then 2 sorry then you will have 2 Mn2 plus 8H water, 8 moles of water. So the electrons will be cancelled out and the final equation will be let's write this final equation in the box. Okay, so the final equation will be 5 Mg plus 2 MnO4 minus plus 16H plus ions, and then it forms 5 moles of Mg2 plus 2 Mn2 plus 8 moles of water. So this is your equation for this reaction. Okay, now predict how the cell reaction will change, if at all, when the solution of magnesium 2 plus half cell is diluted by addition of a large volume of water. Okay, so when the large volume of water is added. Okay, so you can see um, this. Okay, let's see. This is the reaction magnesium 2 plus 2 electrons. Okay, so it is saying that predict how the cell direction will change, if at all, when the solution of magnesium 2 plus ions, this half cell, is diluted by addition of large volume of water. Okay, so when the large volume of water is added, okay, so what will be the effect on this reaction? Okay, so there will be no change because dilution will make this potential even more negative. Okay, um, okay, so there will be no change. Okay, because dilution will make this reaction move to the backward. Okay, this dilution will make this magnesium more soluble. Okay, so that's why this magnesium 2 plus ion will this there will be more oxidation, so this this reduction potential will be more negative for this magnesium half cell. So this the cell electrode will be more positive. Okay, so no change. So no change because dilution will make this half cell, magnesium half cell, potential even more negative. Okay, now moving towards next part B. The molten magnesium salt is electrolyzed for 15 minutes by a constant current. Okay, 4 point okay 4.75 into 10 to the power 22 magnesium atoms are produced at cathode. Okay, calculate the value of current. Okay, you have to find the current. So Q is equals to IT. So you have to find the current. You are given the time. So if you calculate the charge, you will calculate the current. Okay, and this is the reaction on the of the magnesium at cathode. This magnesium 2 plus ions gains 2 moles 2 electrons and it forms magnesium. Okay, and you are told that the 4.75 into 10 to the power 22 atoms of magnesium are formed at cathode. Okay, so for the 1 mole of this magnesium mole, for in 1 mole there are 6.2 6.02 into 10 to the power 23 mole atoms, okay, of magnesium. If 1 mole of magnesium is formed, so and what will be the charge on electron in 1 mole? It is the this charge. Okay, this Faraday's constant. Okay, this is the charge on 1 mole of electron. Okay, and there are 2 moles of electrons, so 2 into 96500. Okay, this is the charge when 1 mole of magnesium is formed. Okay, so the electrons will have a charge of 2 into 96500. Okay, so if 4.75 into 10 to the power 22 atoms are produced, what will be the charge of electron? Okay, so by cross multiplication you will find the charge, and it is going to be 2 into 96500 multiplied by 4.75 into 10 to the power 22 divided by 6.02 into 10 to the power 23. Okay, so x becomes the value of x becomes 15 228. Okay, coulombs. Okay, so this is your charge. Okay, this is the charge. So now you have calculated the charge, so you can calculate the current. Okay, so Q is equals to IT. and I is equals to 15 to 8 divided by time. It's 15 multiplied by 60. So you will get the answer of 16.9 ampere. Okay, this is your final answer, 16.9. Okay, now moving towards question number 4. Okay, the value of solubility product KSP of iron 3 hydroxide is given by the following expression. Okay, calculate the solubility of this iron 3 hydroxide. Okay, so for this reaction, if you see, when this iron 3 hydroxide this dissolves, this it forms iron 3 plus Fe3 plus ions and 3 moles of OH ions. Okay, this will be the reaction, and you are told to find the calculate the solubility of this iron 3 hydroxide. So if this X, there are X moles or concentration of iron 3 hydroxide is X, so X moles of iron 3 these ions will form, and 3x moles of this OH ions will form. Okay, so the KSP will actually be X into 3x cube. Okay, so this will be like KSP is equals to 27x cube. Okay, 27 x power 4, sorry, x power 4, and you are also given the value of this KSP. So 27 x power 4 is equals to 2.0 into 10 to power negative 39. So the value of X will give you the solubility of iron hydroxide. So it is going to be 9.27 into 10 to power minus 11. Okay, 9.28 into 10 to power minus 11. Okay, now moving towards next part, calculate the solubility of iron 3 hydroxide in 0.01 mole per dm cube of barium hydroxide. Okay, so this barium hydroxide is soluble. Okay, because down the group in group 2 the solubility of hydroxides increase, so barium hydroxide will completely be soluble into barium 2 plus ions and 2 OH minus ions. Okay, and this iron 3 hydroxide will partially be soluble. Okay, okay, now you have to calculate the solubility of this iron 3 hydroxide in 0.1 mole per dm cube of barium hydroxide. Okay, so you have to actually see that this KSP value will not change because the concentration cannot change the value of KSP. Okay, the KSP value will only be affected by the temperature. Okay, now you have to see the concentration of this OH ion. You can see that the OH ion concentration of OH ion increases in this reaction, so the equilibrium will shift to the left side. Okay, so what will be the you can say the concentration of this barium hydroxide, the OH ions will be 0.02. Okay, so you have to calculate the concentration of Fe3 plus ions. Okay, and these Fe3 plus ions, concentration of Fe3 plus ions will give you the value of KSP. Okay, so the equation will be same. KSP is equals to concentration of Fe3 plus and concentration of OH cube. Okay, KSP is 2.02 2.0 into 10 to power minus 39 is equals to, you are in this question you are not sure what is the concentration of this Fe3 plus ions. Okay, so you have to find this concentration of this Fe3 plus ions. Okay, so concentration of Fe3 plus ions, and the OH ion, concentration of OH ion will be 0.02. Okay, why 0.02? Because this barium one this concentration of barium hydroxide is 0.01, and then it forms 2 moles of hydroxide ions, so it becomes 0.02 mole per dm cube. Okay, and from this equation you will find the solubility of Fe iron 3 hydroxide in barium hydroxide. So it will be 2.5 into 10 to power minus 37. Okay, 2.5 into 10 to power minus 34, sorry, minus 34. Now part 3, the iron 3 hydroxide is less soluble in barium hydroxide than it is in pure water. Okay, so you have to name this effect. Okay, so this effect, so this is actually a common ion effect. This effect is called common ion effect. Okay, because you can see there is a common ion, OH ion is common in both these reactions. Okay, now moving towards next part B, the numerical value of Ka of HBRO is 2 into 10 to power minus 9. X is a solution of HBRO which contains 4 into 10 to power minus 3 mole of HBRO in 100 cm cube of solution. Okay, in this solution, the following equilibrium is established in which there are 2 conjugate acid base pairs. Okay, define conjugate acid base pair. So it is the 2 species which differ by 1 H plus ion. Okay, so 2 species that differ by 1 H plus ion. Okay, now identify the 2 conjugate acid base pairs shown in equation above. So this is acid and this is its conjugate base, and this is base and its is conjugate acid. So these are your 2 acid base pairs. So first acid is HBRO and its conjugate base is BRO minus, and the second acid is H3 plus H3O plus, and its conjugate base, its S base is water. Okay, now moving towards next question, part 3, calculate the pH of solution X. Okay, so you have to calculate the pH of solution X. So it's actually the pH of this Ka of weak acid. Okay, so firstly let's write the equation. Okay, you have to first write this the equation. Okay, HBRO will dissociate H plus BRO minus. Okay, BRO minus. Okay, so this is your equation, and the Ka will be, acid dissociation constant will be equals to concentration of these products H plus ions and BRO minus ions upon concentration of HBRO. Okay, so now you have to find the pH. Okay, so firstly we will find the concentration of H plus ions. Okay, so this you can say that these both H plus ions and BRO minus are produced in equal amounts, so you can write this equation this as this. Okay, this as well in this form. Now it will be easier to find the concentration of H plus ions. Okay, so H plus ions, concentration of H plus ions is equals to Ka multiplied by concentration of HbRO and square root. Okay, so what is the concentration of HbRO? This is the 4 moles, 4 into 10 to the power minus 3 moles in 100 cm cube. Okay, so it's actually like this. Okay, let's calculate it, and the value of Ka is also given to you, which is 2 into 10 to the power 9, 2 into 10 to the power minus 9, and the concentration of HbRO is 4 into 10 to the power minus 3 moles in 100 cm cube. So you will there will be 1000 divided by 100. Okay, so and we will take the cube root of this. So the concentration of H plus ions will be, the concentration of H plus ions will be 8.94 into 10 to the power minus 6. Okay, so the concentration of H plus ion, now you have calculated it. Now the pH is equals to minus log concentration of H plus ions. So it is going to be minus log concentration of H plus ions 8.94 into 10 to the power minus 6. It is going to be a 5.05. Okay, this is your pH. Now the solution containing 2 into 10 to the power minus 3 mole of NaOH is added to solution X. Okay, so a buffer solution is formed. Okay, calculate the pH of this buffer solution. So when NaOH is added to HbRO, okay, this solution X contains HbRO, so it will form NaBrO plus H2O. Okay, and there are 2 into 10 to the power minus 3 moles of NaOH. Okay, and what are the moles of HbRO? Okay, the moles of HbRO are 4.4 into 10 to the power minus 3. Okay, 4.0 into 10 to the power minus 3. Okay, so how in 100 cm cube? Okay, these are both in 100 cm cube. Okay, you have to remember this. So now let's see which one of these is in excess. Okay, so this HbRO, moles of HbRO at the end will be 2 into 10 to the power minus 3, and the moles of NaOH will be 0. Okay, and this moles of NaBrO that formed will be 2 into 10 to the power minus 3. Okay, now the Ka, the value of Ka is also given. Okay, which is Ka is 2 into 10 to the power minus 9. Okay, and if you write the equations of these individual reactions, so the HbRO will actually decompose into H plus and BrO minus. Okay, and this NaBrO, okay, this NaBrO will be like this. Okay, Na plus and BrO minus. Okay, so this is also again a common ion effect, and you can see that this BrO, concentration of BrO increases, so the reaction in this part will shift to the left side. Okay, so the concentration of this BrO from this HbRO will be very negligible, so we will not consider it. We will consider the concentration of this BrO. Okay, so again write the expression of Ka. So the Ka is actually equals to concentration of H plus ions plus multiply by concentration of BrO minus divided by concentration of HBRO. But now these H plus ions, concentration of H plus ions and BRO minus will not be the same. Like we did this in this question, the concentration of H plus ions and BRO minus was the same. But in this reaction, it will not be same because BRO is coming from two sources. Okay, so how you will calculate the value of H plus ions? So this concentration of BRO is actually equals to this concentration of NaBRO. Okay, because this BRO is very negligible. Concentration of this BRO is very negligible. So this BRO is the main source of BRO negative is actually from this NaBRO. So the concentration of NaBRO will be equal to the concentration of BRO minus. So we can actually write it as, so what is the concentration of this NaBRO? So it's actually you are given the moles 2 into 10 to the power minus 3 and 100 cm cube. Okay, so but you are not required to convert it into 100 into 100 cm cube because these all are in 100 cm cube. Okay, so you can ignore this. Okay, and what is the value of Ka? It's 2.0 into 10 to the power minus 9. And concentration of H plus ions, you have to find out this concentration, and the concentration of Br minus will be 2 into 10 to the power minus 3. I'm writing here the moles. Okay, it's actually not the concentration, but this volume is constant, it's 100 cm cube. Okay, so we are ignoring it, and this concentration of HBRO at the end is 2 into 10 to the power minus 3. Okay, this concentration. Okay, so this cancel out with this, and the concentration of H plus ions is equals to 2 into 10 to the power minus 9. Okay, now you have to calculate the pH. pH is equals to log concentration of H plus ions, so it is going to be 2.0 into 10 to the power minus 9, and the final answer is going to be 8.7. Okay, so this is your final answer, 8.70. This is your final answer. Now moving towards question number 5. Okay, copper is a transition element. It forms a wide variety of compounds. Define transition element. So it is a d block element that forms one or more stable ions with incomplete d orbitals. Okay, a d block element that forms one or more stable ions with incomplete d orbitals. Okay, now part B. An aqueous solution of copper to sulfate contains this complex ions. Okay, if an excess of concentrated hydrochloric acid is added to this solution, a ligand exchange reaction occurs, and this copper complex is formed. Okay, complete table 5.1 to state the geometry, the coordination number of copper, and the bond angle in each of the two complexes. So in this the first complex, the geometry is going to be the octahedral because there are 6 compounds. Okay, octahedral, and in this complex there are 4 chloride ions, so geometry will be tetrahedral, and the coordination number will be 6 because these all water molecules are single ligand, you can say monodentate ligands. Okay, so they will donate their single lone pair of electron. Okay, so the coordination number will be 6, and real chloride ions are also monodentate ligands, so the coordination number will be 4. Okay, and the bond angle in this will be you know that the bond in tetrahedral is 109.5 degree, and in this octahedral the bond angle is 90 degrees. Okay, or you can also write it as a 180-degree. Now moving towards next part. In an isolated copper 2 plus ion, the d orbitals are all degenerated. Okay, degenerate means of same energy level. Okay, and in a complex ion such as this complex ion of copper, the d orbitals are non-degenerate. Okay, define the degenerate and non-degenerate in this context. Okay, so it means degenerate means of same energy level, of the same energy level, and it means of different, not of same energy level or different energy levels, of different energy level, energy levels. Okay, explain why the solutions of the two complex ions in table 1.5.1 are different colors. Okay, of different colors, because the color is given by uh, the energy change between these non-degenerate orbitals. Okay, degenerate orbitals like in complex. So degeneration occurs like this, and this is the energy gap, and the complementary color is given, and the photon, the wavelength or frequency of light which is absorbed by electron is also different. Okay, so that's why the different photon is observed, so the complementary color given will be different. Okay, so you will write different frequency or wavelength, frequency of or wavelength is absorbed. Okay, that's why the complementary color is different, but you are not required to write that, because only 1 marks, this is only 1 marks question. Okay, okay, now part C. Copper 2 plus forms a complex ion containing water molecules and ethane diode ions, okay, as ligands. Okay, and this is ethane diode ion is monodentate, bidentate ligand, and it already told you. The formula of the complex is also given to you. The ethane diode ion is a bidentate ligand. So what is meant by bidentate ligand? It is a ligand which forms two dative bonds to the central metal line. Okay, species which forms which forms two dative bonds to the central metal line, central metal metal ion in the complex. Okay, the one which donate two lone pair of electrons in the to the central metal ion in the complex is called bidentate ligand. Okay, now there are three isomers with the formula this complex. Okay, complete the three-dimensional diagram to show these three stereoisomerisms. Okay, you have to draw the structures of the isomerism. So these all will have octahedral geometry, because the coordination number is actually 6. Okay, so like this. Okay, and this is the ethane diode ion. Okay, so and this ethane diode ion is actually a bidentate ligand. So you have to show it like this. Okay, like let's first draw the optical isomerism. Okay, this will show optical as well as stereoisomerism. Let's see how. C2O4 minus, and the other, let's draw it here, O4 minus. Oh, sorry, not a minus sign. And you will have a water molecule, this water molecule. Okay, now then this is the first isomer and you have to draw the mirror image of this isomer. So that will be your second isomer, C2O4. The mirror image will be like this, and you have this water molecules. Okay, so these are your two mirror images of each other. So this is your optical isomerism. Okay, and now you have to draw the geometrical isomerism. So it will be like this. But how you can tell that which one is cis and which one is trans? Okay, so the one in which the polarity is cancelled out is known as trans. Okay, so in this stereoisomerism 3, you can see that the polarity is cancelled out. Okay, and the bond angle between these same molecules, water molecules, is 180-degree. Okay, but in this stereoisomerism 1 and 2, the polarity is not cancelled out, so these both are cis isomers. Okay, but these are both optical isomers of each other as well. Now part 3, use your answer to C2, sorry, to answer this question. Stereoisomerisms 1, 2 and 3 showed two different types of isomerisms. Okay, name these two types of isomerism. For each type of isomerism, identify the pair of stereoisomerisms that demonstrate this isomerism. So the first type of isomerism is optical isomerism, uh, and it's going to be optical isomerism. So optical, and the second the type of isomerism is geometrical, or you can write it as geometrical or cis and trans. Geometric isomerism. So the first and second pair show the optical isomerism. First and second show the optical isomerism, and then first and third, or second or third, show the first and third, or second and third shows the geometrical isomerism. Okay. Now moving towards next part. Okay, part D. A solution containing 3.7 gram of this compound dissolves in 100 cm cube of solution. Okay, a 25 cm cube sample of this solution is warmed and then oxidized by 0.0 mole per dm cube acidified potassium magnet. Okay, the equation is given to you. Okay, now you have to calculate the minimum volume of acidified potassium magnet needed to oxidize all of the ethane diode in 25 cm cube of sample. Okay, so first you have to calculate this, convert this compound into moles. You are given mass. Okay, so moles is going to be 3.7 divided by 321.5. Okay, because you are this is the MR. Okay, so you will calculate the MR from here. So let's find out the moles. Okay, so number of moles are going to be 0.0115 moles. Okay, but these are the moles of this compound. Okay, this whole compound. These are not the moles of this ethane diode ions. The moles of ethane diode ions will be 0.011 into 10 to multiply by 2. So it is going to be 0.023 moles. Why? Because you can see in this compound there are two molecules of ethane diode ions. Okay, so you will multiply it with 2. So these will be the moles of ethane diode ions. Okay, now this is in 100 cm cube. Okay, you have to convert it into 25 cm cube sample. Okay, so what will be the moles of ethane diode ions in 25 cm cube sample? So you will divide it by 4. 0.02 divided by 4. So the moles in 25 cm cube sample will be 0.0057 moles. Okay, These are in 25 cm cube sample. Okay. Now, what will be the moles of MnO4 from this equation? Because 25 cm cube of this sample reacts with MnO4. So by ratio, we will find the moles. So 2 upon 5 into 0.00575 is equals to the moles of MnO4 needed will be 0.0023. Okay, moles. Now you are given the concentration of potassium magnet. You will find the volume. Okay, so N is equals to CV and V is equals to N upon C. You have calculated the mole 0.0027 divided by concentration 0.01, which is this is the concentration of potassium magnet, and you will multiply it with 1000 because the volume will be in dm cube, so you have to convert it into cm cube. So the final volume will be 230 cm cube. Okay, so this is your minimum volume which is required. Okay, now moving towards next part. Copper to nitrate and barium nitrate both decompose when heated. Okay, copper to nitrate decompose at lower temperature than barium nitrate. Okay, suggest a reason for this difference. So reason would be this copper will be smaller. That's why this will polarize the anion more, or you can say a nitrate ion more. So the less energy will be required. Okay, so you can write copper 2 plus is smaller. So there will be this due to because this is similar, so it will have a higher charge density, so it will polarize the nitrate ion more. Okay, so because this copper 2 plus ion is similar, so there will be more polarization of nitrate ions. Okay, so less energy less energy is required. Okay, now I think that's all for the day. We have done 5 questions and we will do rest of the questions in the next part. Okay, thanks everyone for watching, and if you have any queries until now, you can ask me in the comments. Okay, and we will see you in the next video very soon. Okay, take care and Allah Hafiz.